Hello, I'm Dr. Paul Egan, and today I'm going to be talking about TRIZ, which is also known as the theory of inventive problem solving, which is a systematic method for engineering design to come up with innovative solutions. The content we're going to cover today is going to be over how TRIZ is a systematic approach and a little bit about its history, and then we're going to go over a TRIZ problem with example solutions. And so the key sources are from the Dieter and Schmidt Engineering Design Textbook, which is a common engineering design textbook for undergraduate courses, and also Attila Ertas's Transdisciplinary Engineering Design Process textbook, which also has some information about TRIZ in it. So TRIZ is known as a systematic approach for design problem solving, which is different than something like brainstorming, which can be a little bit more like using random ideas to come up with solutions to problems. So a systematic approach such as TRIZ is going to let us follow the same method or process each time to try and come up with a novel solution to a problem. So for instance, we can look at this equation here, 3x squared plus 5x plus 2 equals 0. And there's multiple ways that we could solve for x. So one way, which would be a non-systematic approach, is we're just going to guess random numbers for x until we come up with a specified solution that solves the problem, which could take a long time if it's a complex problem and not easy to solve. But there's other formulaic methods we can do to reliably get the answer to this equation. So we could use a quadratic equation, we could use a graphing calculator, or we could also factor the polynomial. And so what we're really doing here is we're taking a specific problem, which is 3x squared plus 5x plus 2, and mapping it to an abstraction because we know this form, ax squared plus bx plus c equals 0. We can use specific algebraic techniques, such as a quadratic equation that you see here, and then we can reliably get this specific solution. And so we're going to try and apply this same logic and process to design problems. And so when we're talking about design problems, we're talking about your specific inventive problem. So for instance, your problem might be, I want to design a new car, or I want to design a new airplane or wind turbine. And so we're going to find a way to reliably use TRIZ to come up with innovations to solve that problem in a new way. So how we're going to solve this specific inventive problem, rather than using trial and error and brainstorming, which isn't going to reliably get us the best or innovative solutions, we're going to use a TRIZ mapping to solve the problem. So we're going to take our specific inventive problem and then map it to an abstract problem category. So such as for the car, I want the car to go faster while not being heavier. And then TRIZ tools and techniques will give us suggested solutions for that abstract problem category based on how other people have solved that design contradiction or trade-off based on past evidence and patents. And then we're going to apply that logic and design principles from TRIZ to the specific inventive solution for the car or wind turbine or whatever else you're trying to design to come up with an innovation by following this pattern. And so this brings us to talking about TRIZ in more detail, which is often referred to as a theory of inventive problem solving, so that we can take our problems and come up with inventions that are innovative and will improve the state of the art in the field. So a little bit about the history of TRIZ. TRIZ is a Russian acronym that was developed by a team in Russia between 1946 and 1985. That's a problem-solving methodology that was built on studying patterns of problem using logic, data, and research, rather than just focusing on creativity and brainstorming and non-systematic methods of individual or groups. And so they did this by studying more than 3 million patents that were analyzed to discover patterns. So these became TRIZ principles that you can apply to problems repeatedly that allows you to come up with innovative solutions. So how TRIZ works is you want to start with identifying a specific design problem with constraints or contradictions That's how we represent design problems in engineering design that has trade-offs. And then you want to reformulate those trade-offs as general contradictions. For example, you want to increase the speed of your system without increasing the weight. So we can think of a lot of different designs where you might want to increase the speed without increasing the weight. And those would all be able to be plugged into this TRIZ system to see what principles apply to try and improve it. And so we'll see more of these details on the coming slides. So with TRIZ, you need to map your contradictions to these 39 TRIZ contradictions. So from your specific system, you want to find trade-offs that would fit into this TRIZ framework, because once you can map it to this TRIZ framework, then you can solve what's called the TRIZ contradiction matrix to see what design principles might solve the contradictions and trade-offs in your system. So here you might want to say weight of moving object, number 1, that's what you want to improve. But number 32, manufacturability, you don't want that to be any worse as you move forward with your system. And so the next step is to convert your problem to the TRIZ general problem. And so another example of contradiction is you want a magnetic tool to be long enough to reach objects, but also so that it is short enough to carry. So how can we solve this using TRIZ? There's principles of segmentation in TRIZ, which if you map this, you want it to be long without compromising its length. You could plug this into TRIZ and it'll give you principles such as segmentation, which then you take that magnetic tool and realize you could make a telescoping rod, which can become longer and shorter based on how you need to use it or carry it. So what you want to do next in TRIZ is solve the contradictions to find which TRIZ principles can help you improve your design problem solution. So here we're going to convert a TRIZ contradiction of we want to increase power while not increasing weight. And we look at this TRIZ matrix, which is going to be the same for every single TRIZ problem you solve. So if we're going to improve a feature, 21 power, we see that at the bottom row highlighted. And then to the right, we see worsening features. And so number 1, weight of moving object, that's the first column there. So we match row 21 to column 1. And we circle that solution, and we see that TRIZ principles 8, 36, 38, and 31 could all apply to help solve this problem. And in total, there's 40 TRIZ principles, inventive principles that help you solve the problem. And so the matrix, based on the contradictions you have, will point out different inventive principles from these 40 that'll help you solve that problem. So here's a highlighting of some of the most common TRIZ principles applied. And so you can look on different online sources or textbooks, and they'll give you more details about each of the 40 TRIZ principles and how they could apply to your problem. So some of the most common TRIZ principles are number 1, segmentation, and number 2, extraction, which you can see illustrated up here are also renamed number 1, division, and number 2, taking out. So depending on the source you use, there might be a different translation or semantics difference. And so it could be good to look at multiple sources to help you have more ideas to solve the problem. But here, for instance, taking out number 2, you can see this illustration of a boat where the motor in the boat is too noisy. So you want to reduce the noise of the motor in the boat. But one of the examples from the TRIZ principles is rather than trying to reduce the noise in the boat, you could take that component and just move it outside to follow the boat so that you could keep the same noise level, but it's a lower noise within the boat where the people would be affected. So that's an innovative way of solving the problem rather than doing a compromise such as taking that component and making it quieter by reducing its power or other features that might not be desirable. So because the TRIZ matrix is always the same, as long as you get the trade-offs and know which numbered contradictions they are, you can go to a resource such as triz40.com and it allows you to put it in automatically. So here we have 2 weight of stationary to improve while not hurting 39 capacity/productivity. And then we get different suggested principles of segmentation, mechanics substitution, dynamics, and parameter changes to solve that problem. So if you want to use TRIZ repeatedly and look at a lot of different solutions, using a tool online or otherwise could be helpful. And so the last step of TRIZ is you want to use the inventive principles that are general to help ideate for your specific problem. So once you come up with those principles to solve that contradiction, you want to think back to your original problem, which might have been designing a new car or wind turbine, and seeing how those principles will apply from there, using the same logic and how it applied in the examples such as the boat we talked about. So here's a little example. If you wanted to improve the weight of an aerospace material for an airplane body, we could look at the corresponding TRIZ principles to solve the contradiction. So here we're going to say we want to improve weight, number 1. So we go into row number 1, and then we move it to column 14. We don't want to worsen strength. And so we get TRIZ principles 28, 27, 18, and 40 out of the matrix. And so from these 4 principles, can you ideate solutions based on these principles? So 18 is mechanical vibration, 27 is inexpensive short life, 28 is replacement of mechanical system, and 40 is composite materials. So here, 40 composite materials make sense for an airplane because you could use carbon fiber instead of steel or aluminum for parts. But also if you were flying an airplane or other system and it wasn't going to be in service for a long time, you could use disposable components or something that also might not compromise the weight, or different ways of replacing the mechanical system, or with mechanical vibration, reducing the force different components might experience by absorbing the load with some kind of spring energy so that you reduce the fatigue life of the system. So you can see from here, even though 40 might be the most obvious principle to apply, there's still innovations to think about when covering the other principles as well. And so here's a little listing of the different principles and some examples of how that could work. So 27, material is high performance but needs replacement after damage. 18 uses spring system to reduce total forces experienced. 28, rearrange inside components of aircraft to reduce body strength needs. And 40 is use a composite material that is stronger and lighter than the previous material you considered. And so we're going to look more in depth at an example here that's a practice problem for metal flow through a pipe. And so the example problem is metal powder flows through a pipe and impinges on the bend, causing erosion. We want to increase flow without causing damage. So you can see these star-shaped particles that represents a metal powder, and as it's flowing through the pipe, it hits that corner and it's going to erode it over time, which might require a pipe replacement or might damage the pipe. So how can we use TRIZ to solve this? And this is where you might want to pause the video and go through TRIZ yourself to see if you can solve it before comparing with what we do next. And so solving the contradiction, we want to improve speed without degrading force, durability, losing matter, or reducing quantity. And so improve speed 9 is the first part of our contradiction. And then we don't want to worsen force, durability, loss of matter, or quantity of substance, which all map to different TRIZ contradictions. So 10, 15, 23, and 26. So then you would go to triz40.com or look at the generalized matrix in a textbook and say you want to improve 9 without worsening 10, 15, 23, or 26. And then for each of those combinations, you get a list of 4 principles to be applied to eliminate the contradiction. And so from those, we can get different solutions to ideate. So from principle 13, we'd get inversion, which requires the designer to look at the problem in reverse or the other way around. So in this problem, we could look at the next step of the processing of the metal powder and see what kind of solution can come from bringing materials for the next step to the location of the material powder, so it doesn't even need to go through the pipe in the first place. So this eliminates the contradiction by removing the need to transport the powder through any kind of direction changing flow. You could also, change the location so it still goes through the pipe, but it's not changing the direction as well. So a second solution, principle 15, dynamics, suggests allowing the characteristics of an object to change to become more beneficial to the process and make a rigid or inflexible object movable or adaptable. So we could apply this principle by reducing the elbow bend in the pipe to have a higher wall thickness through the bend so that the erosion of the inner surface won't be compromised based on the structure of the bend. Another option might be to make the bend area elastic so that the medical particles would transmit some of their impact energy to deformation of the system rather than erosion, where the deformation of the system would absorb that energy through movement and then release it in a way that the metal particles weren't hitting that bend in the pipe quite as hard. So some limitations of TRIZ to think about. So when you're considering its use, the inventive principles are guidelines, so they're subject to designer interpretation. The principles can be too general for application in a particular design domain. The designer must develop their own analogs for the design solution for the given problem. And there are differences in the interpretation of TRIZ concepts, which you saw through the different illustrations and wording for the different principles based on which source they took from. And there are some aspects of TRIZ that are less intuitive. But overall, the more that you use TRIZ and become familiar with it, you'll be able to understand how to apply these principles to the problems and map it a little bit faster. So in the same way that you have to practice doing the quadratic equation and different mathematical processes, design in TRIZ takes a little bit of practice as well. And then as you get more comfortable with it, you'll be better able to apply it to different problems and figure out how to make it work. And so that is it for the TRIZ lecture. There's definitely more sources online to take a look at in those textbooks I referred to earlier. So I hope you enjoyed TRIZ and will be able to use it to come up with innovative designs and inventions in the future.